and he was the editor-in-chief of Penny, and also associate editor for many international transactions and journals. And also he is a fellow from different societies, including IEEE, IEPR, OSA, AAAS, ACM, and also very current AAAI fellow. Okay, please join me to welcome Dr. Chellappa.
Well, I have taught for more than 32 years. I came to Hong Kong 2 days ago, and of course, as you know, East Coast in Washington is exactly 12 hours behind. So it's night 2 o'clock for me. And today morning I got up at 1:30 and I've been working since. So when you teach, it's embarrassing if somebody in the audience is sleeping. It's even more embarrassing if you fall asleep. So in case I fall asleep, just wake me up. Okay, so I offered to do this tutorial because I know that the morning slot was taken, and they said, well, we have to keep the folks busy in the afternoon also. So I offered that I graciously accepted. There are some common things between my tutorial and the one that you heard this morning. That was a very good tutorial, by the way, on deep learning networks. So those notes were very well done. And also, the common thing is that we both use data. Both are data-driven things, the ones I'm going to talk about, and the ones that Professor Wang described, so-called deep learning networks. I'm going to talk about dictionaries. And you can view the dictionaries as one-level network. So we don't really do a lot of hierarchical things. We do two-stage things. I can, a little later when we talk about expression recognition and linking expressions with action units, we have two-layer kind of setup. Otherwise, it's just a single layer. Okay. Performance-wise, dictionary methods are not as good as deep learning methods. If people already have 99.63% on LFW, you know, you only have 0.37 left, assuming you don't do better than 100%, right? And so that's where deep learning networks is. And as I was listening to Professor Wang's talk, it looks like it's an exciting area to work on. And Jan LeCun actually in 1989 presented the convolution neural networks. I'm going to give a little bit of history of how all this happened later on. So it's been there. Now, because of all the data that we have, annotated data, as well as GPUs, so we are able to produce results, right? It is said of a warrior that he lives by the sword, he or she will also die by the sword. So if you live by data, you may also die by data. In the sense, if you have to start new data, then you have to start the training. Of course, deep learning networks fail. Once you have trained the network for a certain task, you can take those features and they should be all right for the other task. It's a belief. There's no real mathematical proof to justify that, right? But it does work. As you have seen, LFW performance as well as on ImageNet, it shook up the computer vision folks, the regular folks. So performance does matter, right? But I'm going to talk about a particular way of dealing with data. And I think Professor Wang was saying how computer vision people didn't like CNN. It's not, computer vision people don't like pattern recognition. It's not, they're not any particularly don't like CNN. This is something that has developed over the years. When CVPR first came in 1983, there were just a few papers on pattern recognition. The first conference was in Washington, D.C. And there was just one session on pattern recognition. Otherwise, everything was computer vision. Because at that time, computer vision was a new field. We were doing the regularization thing. We were trying to build 3D models from a single image, from multiple images, object recognition, segmentation. All of these were not solved in the early 80s. So in 1983, we had the first CVPR. 95% of the papers were on computer vision, and 5% were pattern recognition. some paper on fingerprint, some on OCR, some on even speech recognition. So hardcore pattern recognition folks like Bob Haralik and others used to scream and yell at every meeting, how come you ignore pattern recognition? Now if you go to CVPR, there's very little CV, there's very little computer vision in a proper way. Because we seem to have solved the shape from shading problem, we have solved the stereo, structure from motion, right? Object recognition has now turned to become a pattern recognition problem. Get features and then send them through SVMs or deep learning networks. So I asked the question, where is CV in CVPR, right? So in the early days, computer vision people felt that they have to kind of have a PR there because as before CVPR, we used to have a conference known as PRIP, Pattern Recognition and Image Processing. The last conference was in 1982 in Las Vegas, okay? And then they kicked all the IP guys out, the image processing. They said, man, you are just two-dimensional. So the computer vision came and took over, and then they had to keep the PR because the people who were working in PR were very powerful in computer society, so they couldn't fire at that time. So I'm giving all the stories because after having rice for lunch, I think some of you will feel a little sleepy. So I'll kind of keep you humored and then tell you about the technical aspect. But unlike the morning session, please ask questions. I started teaching in 1981. Although my brothers seem to think I started teaching them when I was 16 years old. That's the different story. 1981, so this is 34 years. And I've pretty much seen all students I have to see, right? So just, you won't offend me in any way. Just raise and say, I don't think what you're saying makes sense. You can say that and I'll try to convince you otherwise. Okay, so sparse representations, dictionaries, and domain adaptation. I'll tell you what these mean. So, of course, the application I'm going to focus on is face recognition. You already have heard enough about it, but we'll hear some more. And then the next point I want to make is data-driven versus model-driven. Of course, one can always question these kinds of labels. In the good old days, it used to be said that if it works, it is pattern recognition. If it didn't work, it was artificial intelligence. Levine Kernel at Maryland made that statement. So now it looks like if it works, it's a pattern recognition. It kind of doesn't work in computer vision. You know, I know I'm being recorded, but Ajay has told me that I have the right to erase things. So that's why I'm going to give you all these kinds of statements. So field has changed. We have now become more PR because we have a lot of data, and you know, so that's helpful. Performance matters. You know, computer vision tries to achieve the performance, but deep learning is now really doing well. Okay, so we have to accept that. So we'll talk about representing faces using dictionaries, still faces as well as video faces. In OCR, you know, you don't have a lot of issues with respect to pose. Maybe you have to do 2D alignment, that's fine, but there is, you know, not much of that. Or illumination, because it's a controlled thing. Whereas when it comes to an outdoor face verification problem, the person may not be looking at the camera. And it may be at a distance of 200 meters. Professor Brian Lowell, you know, is also working on similar problems. So there may not be a lot of pixels between the eyes, maybe 15 pixels and so forth. Illumination may not be good. So all these variations are there. Okay, so you have to be able to handle them. And also representing, using linear representation is not always a good idea. Okay, so nonlinearity. Now, domain adaptation is a very old problem with a new name. When you design a pattern recognition machine, you're supposed to do it with the help of a training data set. We talked about learning, you know, so annotated faces with labels, identities given to you, right? It's a training data set. And so you build the system, you put it up, and then you sell it to somebody, and they're going to test it on a completely different database. In fact, we have this issue in face recognition, open set versus closed set. Closed set means you only expect to see the same people again in different poses and different illuminations. Open set, the people are very different. You have not seen them before. What is the simplest method that works for open set recognition? Reserve component analysis. I don't have to know any of your identities. I just take your faces, make vectors out of them, align them, get my identity composition. and then take every one of you and represent it using that coefficients. And then suddenly some new guy shows up, then I want to know if he is there in the gallery or not. I just expand that guy using the same eigen set. I have the coefficients, I compare them. It generalizes to open set, the simplest differential component analysis. On the other hand, if you go to Fisher's linear discriminant, you need to know the identities because you are designing your transformations so that the within class thing is minimized and between classes separated and so forth, right? So now in the case of domain adaptation, so the pattern recognition, you have the issue of training as a specific. So in the case of phase, you can actually look at multiple dimensions. Resolution is an issue, pose is an issue, elimination is an issue, expression is an issue. So every one of them will create a difference in probabilistic distribution of the training versus the testing dataset. So domain adaptation is a way to scale your classifier so that it works with these new transformations. Okay, so we need to discuss that. Okay, so very quickly, I'm not going to take too much time here. PCA, local binary patterns, that was discussed in the morning talk, and I was surprised that it was giving 95% for one of the tasks. And Gabon-Jets, Malsberg did it in 1994 as part of dynamic link architecture. Spherical harmonics, this is out of Bastry and Jacobs. They're basically doing Fourier transforms on a sphere, and it is known to represent illumination variations there. And of course, out of the blue came attributes. Very intuitive. You can describe me as a male, Asian, dark hair, balding, not bald hair, but balding. There's a difference between these two, and etc., etc. And then to the extent you can get enough attributes, you can pin me down. In fact, we can now get 73 attributes very easily. Wearing glasses, not wearing glasses, having mustache, etc., right? So they are very interesting. Of course, deep learning. And recognition methods, we have principal component analysis, Fisher faces, Malsberg's elastic branch graph. Of course, since 96, everything is SVM. If you go to before, 3 years prior to now, if we have gone to CVPR, data, hog, SIP, SERP, and then SVM. Right? That's how. But after 3 order talks, you feel like, is it going to be any different? In fact, sometimes people will say, my features are so good, I'm just happy using linear SVMs. Not that I have anything against SVM. Anything it's a very nice setup. It's okay, it does work well. But now, of course, we have deep learning, and all these guys have contributed to that. There have been methods where pose invariant is not possible, maybe robust, elimination robust, and 3D, building of 3D models, and then there was an effort to use 3D data itself, laser range data. Of course, there's a lot of work that comes from human perception and so on. So, Lance and Better did the 3D Markov models, required manual alignment to get it going. And this is an interesting method that came out of Maryland from David Jacobs and his student Carlos Castillo. This would be A. Basically, if you are given 2 faces to match in verification, you can treat them as a left and the right image of a stereo pair and then calculate the stereo cost and use that for matching. It had reasonable robustness for elimination. And of course, you can also build 3D models and do face alignment and so forth, right? It turns out we are able to handle up to 45 degrees of yaw, but sometimes pitch is 15 degrees, you get into trouble. If everybody looks like this, right, you just see the head, there's not a whole lot to do. So 15 degrees pitch can create problems, whereas yaw, 45 degrees you can handle, okay? And of course, video. Everybody said, well, why do you have to do this in single frame? Why can't you use a video, right? Video surveillance cameras produce videos. So we looked at it a long time ago, and people have built on that. And suppose you have a camera network, if they're overlapping, you can do it. If not, then you do the re-identification and so on. So video, just because there are more frames, it doesn't mean it's always helpful. If there's a lot of motion, if there's a lot of illumination variation, it's questionable. Okay, so where are we with respect to face recognition these days? All these data sets are solid. Pi. Can you imagine sending a paper to CVPR with 65% performance or 80% performance on Pi? It's not going to make it. multiply. Everything is now in the upper 90s. LFW is in the upper 90s. So, as sometimes people like to say, are we solving problems or are we solving the data sets? Right? So, pi, everything is fine. And so you will see a paper in 2015. Actually, there are two papers, right? Professor Wang had a paper, and this is Google, right? So, but still, we have a lot of difficult problems. We just finished something like, let me see if this video works. Okay. Yeah. And I put my students on a boat. This is Baltimore Inner Harbor. And we are about 200 meters away in another boat with cameras with long lenses and so on. And there are computer vision students, so they know that they have to look at the camera. Otherwise, it's not going to work. And just look at the motion, the blur, and the number of pixels between the eyes. It's a tough problem. And just even 15 people, we have, we can't achieve 80%, 90%, and so on. And similarly, something like this. Okay, we are all standing about 50 meters away. And I have this Starbucks walk, coffee walk, and changing pose and so on. Anyway, and this is a typical face that you get. You can see the blur. Okay, so these are still problems that we have to look at. So these are the kind of images you see at that distance. Okay. Now, why did data-driven methods become popular? Because when we started in the mid-80s, computer vision seriously, there were a lot of models. We had models for image formation. Take a 3D object, assume where the illumination source is, assume where the camera is, assume the material of certain kind, and then we produce the image, and given the image, get me the 3D. So model. Structure from motion. Motion models were there. Object, 3D models for objects. Aspect graph. Everything was model based. And suddenly, of course, suddenly it all became data-driven. And if you really look at when that happened, how many of you are familiar with factorization theorem of Tomasi and Canale? Structure from motion. If I want to build a 3D model from a sequence, then you get points from each frame, establish correspondence, and then build the data matrix, and you can show for rigid motion of the moving object, this matrix has a rank of 3. You do an SVD, you will get a shape matrix, you will get the motion matrix, bingo, it's done. Whereas before that, we used to have recursive algorithms, nonlinear, iterative algorithms, and so on. SVD is very simple. MATLAB has it. Just put the input, you get the matrix, and then you get the SVD. So this is a good example where people started realizing that maybe we should not go with a lot of models and a lot of parameters and so on. Because if the parameters are sensitive to variations, then it becomes very difficult. So Canale's method is a good example. Eigenfaces, Fisher faces, right? Those are also data-driven. Graph cuts. Before we did segmentation, MRF models were very popular. MRF models have parameters. How many parameters is there in Shi and Malik's graph cuts? You want to know how many classes of textures are there, that's it. Right? Or you can just even recursively do it. If you look at Shi and Malik's, once you define what the similarity metric should be for two guys to belong to the same, that's it. It's automatic. I mean, it takes time. So it is a purely data-driven method. When we did in the 80s 3D modeling from a face, for a face, we will build this image irradiance equation and then invert it, either using characteristic strip maps, a Berthold horn, or other variational approach and so on. And suddenly comes this paper from Kernel where they had registered images, intensity images and 3D depth maps. Very complicated scenes. And then they learned the mapping between these two. They didn't care about the physics. Okay? Image irradiance equation is all about physics. It comes from bidirectional distribution function, BRDF, chapter whatever from robot vision by Berthold horn. But Saxena and Andrew Ng, they just, we don't care, we just going to treat it as a mapping because they have to be aligned. They're aligned with 3D data as well as a 2D image. And they just learn the regression and they smooth it out using an MRF. And then anytime you give a picture, it just gives you a 3D map. So that's another example. 5,000 such pairings were there. But you know, if the image had slant or tilt, it fell apart. But that's a different story. Why did it fall apart? There is no geometry. When you purely do geometry, data, and you ignore your geometry, you are in trouble. Okay, unless you see the frontal face all the time with zero pitch and zero whatever, you're okay. If there's any such changes, you're going to be in trouble. That's what we showed. And then, of course, we have all of these things. Okay, SVM, is fine, and dictionary deep learning. But I can't say deep learning is a great data-driven method. But in terms of number of parameters, it is on the extreme. They're talking about what, 60 million parameters? The deep phase from CVPR 24. Facebook has 120 million parameters. Just think about that. It's amazing that we're not shocked. Because when you take statistics, that's what I was asking for so while, right? Anytime, let's take the simple Gaussian classifier. You have to estimate the mean vector of class conditional density and the covariance matrix. Covariance matrix is a symmetric. If it is a d by d, how many independent components are there? D into d plus 1 by 2. So Ruda and Hart will tell you, to be able to estimate this covariance matrix, you should at least have 3 times the number of samples. Otherwise, you can't invert it when you do the Gaussian classifier, minimum distance classifier, weighted classifier, sigma inverse, Mahalanobis distance, right? So if the covariance matrix is not stable, you're not going to be able to do the classifier. So when we are taught that if you want to estimate the n parameters, you need to at least have 3 n data samples. And here we are happily sitting with 120 million parameters. Just think about it. It's very interesting. And it works. So that's when it works, it works. So we have to find out what to do about it. Okay. So data-driven methods are becoming popular. When I did my PhD in 1981, I had to share PDP 1145 with 30 other research students. The largest image I could process was 32 by 32. If I have a 128 by 128 picture, I will divide it. And then I have to smooth out the boundaries. Because anytime you do block processing, when you put it back together, you have to do it. And you have to work during weekends. Now you see you have GPUs, you don't have to work during weekends. But in those days, and that machine will go down 6 times a day. So the first thing they taught us was how to boot up this machine. Made all kinds of noises. Okay, now that's not there. So data you can send it through, which is a pretty good thing because I'm somewhat split between model and data. I like to think models are what? They're our projections of what we think, right? Not in geometry. Geometric models are precise. You can't really BS around that. But any other models you want, as Boston Jenkins, the famous time series person, I don't know if I have a slide there or not, used to say, all models are wrong, some are useful. Okay? So model versus data driven, this issue is always there. Now let's look at how the deep networks develop. Because if you are in computer vision, you cannot ignore deep learning networks, forget it. If you ignore it, you try LFW, and if you go with 89%, nobody is going to accept your papers. Right? So it is here. It is here to stay. So I'll tell you how to survive deep learning networks. Okay? It's a nice thing, but this is the problem. CNNs were done by Yang LeCun in 1989. Hinton was doing RBM, restricted Boltzmann machines. Why did this neural deep network came? Because they realized that the old neural network with just a hidden layer, the performance was not there. So they had to add more layers. If they added more layers and they did back propagation as they came down from the top to the down, at the lower levels, the gradients did not change much at all. So the parameters did not change, they got stuck. So Hinton said, let us train each layer separately in unsupervised way and use those parameters as initial conditions and do back prop all over. That is the revolution in terms of deep learning, 2006 work. And that worked well for image learning. But Hinton is not pursuing it. He's also jumped into CNNs, right? Convolutional neural networks. Multiple layers. Okay, that's what the thing is. Whereas with neural network, we had hidden layer, input layer, hidden layer, and the output layer. Okay? So by adding more layers, we are able to get better. In fact, the first time the neural network meeting was held in San Diego in 1987. I was a professor at USC, so I just wanted to go and see what is all this thing about. They expected 500 people, 3,000 people showed up. And it was a great event, okay? And the professor who organized it was a young guy at USC. His name is Bart Costco. He got so excited, he declared, AI is officially dead now, long live neural networks. That's what he said actually in those report. Man, he's a young person, so he wrote hold it against it. And DARPA even had a big program, ADR program, $33 million program. Okay? But then what happened? According to Hinton, SVM showed up. SVM was even simpler. Backpropagation had all this issue of, does it converge? Because there are non-linearities in the neural networks. You remember the threshold elements are there, right? SVM, you just have annotated labels and then you send it. Or if the linear things were not working for you, there are 3 different kernel things you can use. Right? Tangent hyperbolic, polynomial, radial basis function. They give all this boost and everybody was happy. In fact, SVM also made its entry through NIPS. If you go back in the early 90s and so forth, SVM came through NIPS, OCR, US Post Office data set and so forth. But now, by adding more layers, deep learning networks are coming and beating SVM. So this is what I call the revenge of the networks. Right? So, I think Professor Wang was saying a classic issue of overfitting is gone because I have a lot of data and so forth. I'm still not sure. I think it's something that has to be seen. And geometry, neocognitron is something that was in 1980 to provide translation invariants. They will fix the coefficients to be same when they move around the image. But other than that, the whole idea with deep learning is you give me enough data, I'll take care of it, right? Trust me. You give me data, I'll take care of it. But we know when we do things, there are variations. Some are geometry, some are appearance, some are physics-based, and so on. Can the data cover everything? And then can the machine generalize? Okay? So this is my, now that I'm 62 years old, I can make all these kinds of statements, and people seem to think they are right. I'm not sure. Data does not generalize. Models do. The whole idea of pattern recognition is you should be able to generalize for things that are not seen. Suppose I give you 1,000 pictures of Professor Brian Level's frontal face. We won't be able to predict how his face will look like when the yaw pitch varies by 20-30 degrees. On the other hand, if I put a 3D model to his face using the frontal faces, I can probably rotate the model around and do some texture mapping and say how it looks. That's all I'm saying. So data does not generalize, whereas models do. So that is something to keep in. So let's look at although I'm going to talk about dictionary, I thought I'll just show you. This is the standard thing: impressive results, best performance, and so on. And this is something that came out of Berkeley from Professor Malik's full lecture. Professor Malik was skeptical about deep learning networks. In a meeting in 2001, when Andrew Ng presented his work, Professor Malik jumped all over him. Now Professor Malik is doing RCN because it works. Just look at the plots for the Pascal thing, right? This is a deformable part model, Felsen Schwab, Deva Raman, and so on. Histogram, gradients, okay? And now where are we? 2014, RCN. Okay? So all my PhD students want to do RCN, CNN, something like this. So wait. You have to add something. If you want to work in a deep learning network now, just think about it. It is producing good performance on a couple of data sets. So you are tempted to do that. People are not going to give you credit for inventing CNNs. Jan LeCun did it, Hinton brought it. So you are bounded from that side. And Google is going to beat you. If you come with 99.2, 3 weeks later they'll have 99.6. But Google is a big place. I was there the other day. There are young people with PhDs running around excited. Three free meals every day. Breakfast, lunch, dinner. And they complain that the dinner options are not that good. But lunch, coffee, you can get Bombay chai. Good. So I was there, sometime in February. First day I asked myself, you are within 50 feet of food. and bring, irrespective of where you are in the Google complex. Okay? So they have a lot of resources. So you cannot beat Google in performance if performance depends on having large data. Right? Facebook, CVPR 2014, 4 million faces to train their deep face, 1,000 people, each 4,000. Why? Because all you young ones put your faces to them. I need your faces to train my machine. You say, oh, privacy, can't do it. But then you put, oh, I went to Hong Kong, look at my picture here. Then Facebook uses all of them and trains their deep networks and they beat me. Think about it. Next time when you put a face. That's why this 99.23, 99.24 is all coming, because you young ones. I won't put, I'm sorry, I'm also on Facebook now. But there's only one picture of me. I know if I put more faces there, then the performance is going to go up. So I just said, I'll give you only one picture. Okay, you can look it up. Chellappa and Facebook, there's one picture which you will see in my I2P transaction. I'm not going to let them generalize anything more than I want, because they come and beat me up. Now I have to find a better method. Anyway, so data-driven method is here to stay. So then you can ask me, so Professor, what can I work on? There are still enough things. Ask yourself, do I really need millions of faces? Humans don't need that many to generalize. A child of age 2, just give a couple of samples of cup. That's a cup, period. You can even put a newspaper on it, ask a kid, where is the cup? It will pull the paper out and show it's right there. So think of methods where you can generalize from as few samples as you can. Think of methods that will have fewer parameters, not every time 60 million, 120 million. Whenever I hear that, my body shakes, because I got trained in statistics. So, those are the things where university people can help. You can compete with Google and Facebook on data. Forget it. It's not happening. And the basic things have already been done. So you have to figure out. So, think about those things, right? And of course, so models. How do you incorporate invariance in networks? So I designed this deep network for this particular task. And then there is the other task. You can't just assume, oh, I'll take the same feature, it should be all right. No, you can't. That is a big leap of faith. So you should know what the distribution of the new data is, what the distribution of the old data is, how I can domain shift one network from this. So those are things you can, small scale problems you can contribute, right? So keep that in mind as you're working for your PhD. Anyway, models are typically computationally efficient, allow us generalization to unseen data. I would, we drive cars. Well, how many of us would like to go under the hood and see what's inside the car? When is it useful? If the car breaks down, it's useful, right? Otherwise, you can happily drive. You don't have to know how the car works. So the idea of having models is, when things don't work, you kind of know what's happening. Why, which part of the model is not working. So that is good. And sometimes it really helps to understand error-driven method. This is a beautiful example by Steve Mala. Okay? All right. So, recognition, reconstruction, and recognition. This is something that Professor Malik also talked about. We had talked about all of these guys, but deep learning networks also allow you to reconstruct. Professor Wang showed examples of that. So now let's talk about dictionaries. Well, you may say, Professor Chellappa, why should I worry about dictionaries? You told us it's not working as well as deep learning networks, so should I waste my time? Well, dictionaries are working well given the fact it's a one-layer thing. Maybe we can think of multiple layers. That is something that can happen. But I still like that because the mathematics is clean. You can go and look and see what you can do with it, and so on. So at most we have only tried 2 layers. And the reason why we got interested in it because of various reasons. I actually wrote a paper on dictionaries in 1999, so I didn't realize it. Somebody else reminded me that, so we have been into that. Of course, sparse representation is something that everybody is interested in. And this is also a data-driven method, but it allows models to be explicitly put. Okay? So these are some of the works that we motivated. Many of you may have seen this work from Berkeley and Illinois. It appeared in PAMI. And we used that for a large IRIS problem. And then we also used it for a face verification problem where elimination variations can be explicitly incorporated. So I'm going to tell you that if performance is something that you want, if your boss says, in the next 4 months, you got to make 99% for this particular image classification problem, otherwise I'll fire you. Then what should you do? Keep running it. Take cafe. Make sure you have a very, very powerful computer. And if you have people who are working for you, then give them the task of annotation. Face, identity, or whatever annotation. Run it through cafe. Code is available. You might, maybe not 99, you'll at least get 90. But if the boss says, don't worry about the performance, I want you to really think about this problem and understand, then you should use dictionaries. Okay? Yeah. Alright. Okay. Are you with me now? Okay, good. Yeah, please ask me questions. You know, I feel very threatened if nobody asks any questions. Just ask me questions. Okay, alright. Okay, so we will, what is this dictionary is all about? Let me take all of your faces. Let's assume I have 5 of Jai here, 4 of Brian, and so forth. That is Xij. I is the identity variable, J is the number of faces I have. And I put them all together and make my matrix T. And then I want to know if Chellappa is here. So what? This is not my idea. This is from right and left. So I write Chellappa Y. That's a linear weighted sums of all of you. Xij. Okay. L faces, L number of people, etc. You may say, why is that? Why should Chellappa be a linear sum of all of you? Well, it's a face. We all have noses, we all have eyes, foreheads, and so on. So let's assume it's okay. Well, what happens if Chellappa is also one of you? Where I was sitting there and my picture was taken and I suddenly show up here. Then only alpha corresponding to that will be non-zero. Everybody else will be 0. So alpha is a sparse vector. So if I can come up with a method for estimating, alpha, sparsest alpha, as lot of non-zero, very, 0, it's sparse. Okay, lot of 0 things. Then I want to find a particular alpha that minimizes 0 now. Imagine a 0 here instead of 1, subject to the condition that Chellappa is a linear combination of everybody here. Of course, that is NP hard. We say let's replace 0 norm with 1, L1 norm. There are cases when that is reasonable. So this becomes a basis pursuit problem, BPDA. You can even assume some noise is present. It's a linear programming problem. I have all of you as a training data set, so I need your identity, so the supervised method. I put it here, and then I write it like this. So I estimate my alpha. Then I can go here, D is known, all of you, A, B, D. Think of D as a Facebook. That's what it is. D is basically a Facebook. Right? And then I can synthesize, and I can find the difference between the synthesized one and the images that are there already. Whichever has the lowest error, I assign. That's basically how the dictionary works. It's pretty simple, right? Actually, it was, when it first came in 2009 in PAMI, they were quite happy because it was robust to occlusion, but it didn't take into account any elimination issues. Okay. And how do you learn your dictionaries? The sparse coding method, this is how you learn, right? Y minus dx, subject to the fact that there is the sparsity constraint, and you can put it in the linear programming problem. Now, there are a couple of methods available for learning dictionaries. When I said D, I assume all of your faces will go there. Room is a little warm, is it? No, you feel a little warm or? Yeah, it's okay. I thought just that my thought is making you all a little warm. Okay, yeah. Anyway. And Y and through Y are training samples. X is a sparse code. So you can alternately learn sparse X and D and so on, and you build your dictionaries. So this is a standard method. There's a couple of methods that are available in the literature. How many of you have heard of KSVD? Yeah. Okay. The KSVD are method of optimal directions. So basically, given a training data set B that I have written here, see a pointer somewhere. Can you see the red dot? Yeah. So B is all of this, and then I want to find D and the sparse coefficients tau, and there is this condition. You have to come up with the sparsity condition, okay? And then there are two steps. One is the sparse coding stage, another one is the update stage using SVD. So this is a fairly simpler method, and it was a journal paper written later. It first came in 2006 by these guys from Israel. Okay, so the idea is, given training samples, we know how to build the dictionary D, and then once you build the dictionary D, you can make the testing sample as a linear function of D, and then estimate the sparse coefficients and do the classification. Fine. But what if my Y has a different illumination? How do you handle that? Because just like deep learning networks, dictionaries cannot handle things it does not. But if I keep feeding the dictionary learning process by all possible variations of illuminated faces, then maybe there is a hope that you can manage illumination variation. So for that, what we do is, we have an input image right here. We want to relit the face so that I can produce multiple illuminations, and then I can feed it to the dictionary learning. This is what we call as data augmentation. In the case of Facebook and so on, you provide all these images in various illumination, various resolution, and so forth. But you don't give me those, so I need to generate them myself. So if I have a good face of you, I can build a 3D model, I can vary the illumination source, I can build all kinds of faces at a different illumination. I feed them to the learning thing. So you can imagine in a deep learning setup, instead of asking for 1 million faces, now you may only have 10,000 faces, and then you can augment the data. Because once you build a 3D model, you can put the texture map and you can illuminate it. You can rotate it every 5 degrees, 2 degrees, 3 degrees around the pitch, yaw, and roll. You can produce a lot of data, synthetic data. Okay, so that is one way you can also address the issue. What if I don't have a lot of training data? Can I still apply deep learning network? For example, in the case of synthetic aperture radar classification problem, SAR, which is a radar, right? The physics is precise. You can actually predict, given the model of the object and the radar characteristics, how the signature will look like as the object rotates. It's very easy. It's a physics, electromagnetic theory. So you can synthetically generate as many data samples as you need for the learning process. That is one of the things that the deep learning people have to realize. Go ahead.
The physics is correct only the model is accurate, right?
Yeah. It's always like
wrong, the physics is
model is wrong, everything goes. For example, in the deep learning, if your annotation is wrong, it's a problem too. It's always like that. As I said, when you depend on data, the data has to be clean. Otherwise, it's going to be a problem. But in the case of dictionaries, what we can do is, if we have ambiguous labels, you say it's not really Chellappa, but I think 80%, 8.8 Chellappa, 0.2 Brian, then we have methods for handling that using expectation maximization approach and so forth. See, that's what it is. If you have If you know what's going on inside, then you can turn the knobs. But if it comes, although deep learning folks want to feel like it is not a black box, but it is kind of a box. Maybe not black, but it's kind of a box, right? Anyway, so if you have a frontal image, what you can do is look at the forward process, right? You have the surface normals, texture map, light source, it produces the intensity image. We want to reverse the process. And you can, this is the simple image variance equation. So models. Actually, you can do this for deep learning also, because this is just a model, how a face looks like from its 3D map, illumination source, and the texture map. And then you can rewrite, this is the observed picture. You can create an initial estimate of albedo using a generic 3D model of the face, Better's database, and a light source. There are methods available for estimating the light source. And then you can write this guy in terms of true albedo, right here, and a signal dependent noise, which will allow you to estimate what this albedo is. So you can write like this. Okay, so once you estimate albedo, you can estimate the shape, and then you can synthesize. Now, how many different illumination images you have to synthesize for each person? Should I do infinite spaces, infinite phases, or is there a fixed number? Professor Kriegman at San Diego and his students showed that it is enough to produce 9 illuminated phases. Okay? So if there is one Chellappa, you can now produce 9 Chellappa phases using this method for various illumination, and your dictionary learning should do better. Okay? You can also do similar things for face, because I have a 3D model. I can rotate it. So this way, you can address the issue of not being a Facebook or a Google. In the sense, you don't have so much data. LFW has enough data. I mean, a lot of universities are using it. But that LFW is a solved problem now. You are not going to become famous going from 99.63 to 99.83. It's not going to happen. Okay, because people who are already in 0.63, they may add one more layer and they'll become 0.9. So you can't compete with Google on it. So forget it. LFW is done. Okay, so you have to think about other problems that you can solve, right? So some of these ideas will be useful even in that context. Okay, anyway, we at a very early age we realized that we're not going to win the LFW battle, so we never even worried about the data set. Of course, we use it for some other problems, for ambiguously labeled dictionary learning and so on. But for verification, the moment I saw the paper coming from somewhere in 92, I said, it is done. It's a matter of time before it will be 99. You just saw Professor White's references. Just in 2014, there was a paper with 95% using LBP, and then within a year it became 99. You can't run that race, right? Because it's just very difficult. So you don't have to. But people still, performance is important. But if you, in fact, if you look at the CVPR, I don't know how many of you are reviewing papers for CVPR. Some of you here. There are instructions now coming. Don't just look at the numbers. Look at the method. Look at the novelty also. Even if the performance is not as great as state of the art, if it is good and if it has a potential of improving, let's accept that. Because what we are worried now is everybody is looking for 1% improvement, otherwise they say reject. Then it becomes a hack. You add the feature dimension, you add this, you add more layers, and they're like SIGGRAPH folks. People who submit for SIGGRAPH, they sleep 9 months. 3 months before the deadline, they wake up. They work 18 hours a day, have 3 papers for SIGGRAPH, they're done, and then they go to sleep again for another 9 months. So with computer vision, if the percentage improvement becomes very important, that's what we are going to be doing, and we won't produce new ideas. So the community has to be receptive for no way of looking at the problem. But listen, if after a certain number of years the performance don't improve, it's going to die on its own. You can't just prop up a dead horse and hope to ride it again, right? It's done. But at least we are understanding that now. See, in the 80s it used to be like that for image compression. Image compression, when you do that, the one measure to evaluate the so-called peak signal to noise ratio, PSNR. If there is 0.5 dB improvement, they will accept it as a conference paper. 1 dB improvement, journal paper. 3 dB improvement, you get an award. So everybody will take that image, and just beat it to get 1 dB improvement and so on. And it becomes a hack. So, that's really not good for the field. Okay, another thing is resolution. I remember when this method was discussed at BTAS, Brian had a very good question. You got to align them. How are you going to get your eye centers if the thing is so bad? That's the problem. That's why it's not done yet, right? Because alignment is still a big problem, irrespective of what method you use. Although the most recent CVPR method claims that they don't care about alignment because they're doing patch-based method and so on. Yeah, but typically we need to have good alignment. So if you have dictionaries, you can actually, high resolution, you can synthesize low resolution dictionaries because there is a model how you produce low resolution images and so on, so you can match in the resolution space. And you can also handle in-plane rotation by building dictionaries in the Radon transform and so on. So my point is, if you have an underlying mathematics that you can go ahead.
Oh, just, Jim Wayman, he said in the speech community, it was well known that you can't fake bad data by getting good data and manipulating it. Because we had a problem that we had good data sets and we made them low resolution. And we got really good performance on there. But when we tried data that was the same resolution that was actually captured, it didn't work. And one of the reasons is if you start with a very high resolution, you don't understand all the reasons, but one reason is you can start with a beautifully aligned ferret set. The eyes have been placed exactly at the right spot, and when you photo reduce it, everything's very well aligned. But if you start with that low-res data, where the eyes are basically 1 pixel wide, you don't know where the eyes should be, so you can't, so one thing is you can't get the alignment right compared to the, if you started with high-res and did it. So back to the Jim Wayman rule, you can't fake bad data.
That is true, but if you have low resolution, the idea of doing super resolution is not going to work either.
It doesn't work either.
Yeah. So between two evils, you got to go with one that is possible. But Derek Gold claims he has a very good eye detection algorithm for blurred faces. So I like that approach better than trying to make the low resolution become super resolution. Super resolution works for a factor of 2, I think. That's about it. Even then, it introduces artifacts. So I agree. But the thing is, though, if you have a very high resolution gallery, we can produce a good low resolution images. But we have to keep track of the fact where the eyes go. But then, when the low resolution picture is there to match, if that is not aligned to the one that you are producing from your gallery, you are in trouble. So I would say methods like LPP and so on, they seem to be a little bit reasonable with respect to misalignments. But no, that's the problem. That's why face recognition is not solved, right? So that's still an issue. Okay, now that's a good point. The dictionaries, we did it for still. We can also do it for videos because videos are available. So what you do is you take a video, the gallery and the probe, and you segment them along various poses. Okay, like you can do an algorithm that's a generalization of keyframe selection, and then you will view each such cluster as the original image, like a still image, and then you build your video dictionaries, and the method is the same. Mathematics is a little bit more complicated when you go to videos, but look at the performance. Okay, this is MEGC data set where a person moves towards the camera and the last few seconds turns around. Okay? And as you can see, it's a dark corridor. Even the face is not visible. Okay? It's an image collected at Notre Dame, and there are all these methods. 146 subjects, various protocols. People started at 30 to 38%. Slowly it comes to around 79 and so on. And then you can improve, and looks like performance only goes up, right? So we like to say, but then if you have a slightly different protocol, you can reach the magical 90 plus for the various So the dictionary methods can produce reasonable results. The other data set here is from University of Texas at Dallas, Fox videos, unconstrained. Okay, the face is only a small component of the entire body, and you have 510 walking, frontal, and activity profile face. Activity means like this. They are talking. As you can see, it's not frontal, so it's pretty challenging. And if you look at the performance for this, they are best is 62. So people talk about 95 and so on for YouTube. YouTube is a more benign data set than the data set from UT Dallas, because the activity phases, they're not looking at the camera. It's almost like a profile view. So I want you to know that face recognition is not solved. There are still data sets in the public domain where the performance is not good enough for deployment. Okay, so don't get the view that, all right, LFW 99, we are done, so I want to change my thesis topic. No, you give me a face verification algorithm, I'll give you phases where you will fail. That's the beauty of this problem. As you can see, the performance here still is very low. Okay. Now, of course, we also tried it on, these are various methods for the rockers, for verification and so on. We tried it. If you want upper 90s for a video problem, which data set should you try? Can't try UCSD data. That's now done, so don't do it. It's done. This Buffy data set is still tricky. And the YouTube, people are now getting, there are different kinds of YouTube data sets. In 95, and with our dictionaries, we are not reaching 95. I'm only in the 80s. Okay? But this got accepted in BMBC. They said, well, your performance is not up to mark, but we like the method. So the reviewers are warming up to the idea that, not everybody has to come with the 2% better than what is the state of the art. But you can do it only for a while. After that, it has to improve. So we are working on this. So you can see for Buffy data set, still in the upper 80s. Okay. All right. Now, when I wrote down my picture as a linear combination, the question is, why should it be linear? Can I think of, just like in the case of SVM, when we went from linear SVM to kernel SVMs, can dictionaries be non-linear? In the case of deep learning networks, neural networks, non-linearity comes because of the threshold devices. In the case of deep learning networks, non-linearity comes when you do the max tool. Right? They take a convolution, they do the max of that. So non-linear operation is important in these things. You can do it very simply as follows. You can now, instead of writing y minus dx, you just write a kernel, phi of y. You don't have to exactly specify what the kernel here could be. It could be one of the three things that we have looked at, polynomial kernel, it could be areal basis function, and so forth. And you can go through the same dictionary learning procedure, and this nonlinear generalization usually allows you, as you can see, just like in the case of SVM, the phi doesn't explicitly come, it just comes through the kernel k, z. So this can be a polynomial or tangent things and so forth. Okay? So now, these are some math that we can skip for the afternoon. So this is the USPS data set. When you do the nonlinear generalization, the percentage improves at least by a few percent points. And this is in NIPS. If you want to have a paper in NIPS, you got to try your method on the USPS digit data sets, and you can do all kinds of Caltech 101. This is a bit dated. Things are much better now. With nonlinear dictionaries, you are achieving about 80%. Now people have upper 90s on this data set. and then face recognition, AR, and so forth. These are all much higher now. This is from a couple of years ago. Everything here is now 98 and things like that. Gender also is in the mid upper 90s. So that's so nonlinear extension usually gives you a few percent improvement. Now, when I introduced the concept of dictionary, we just talked about one layer. I wrote Y as sigma of xi, right? There is no multiple layer. Is there a reason sometimes to provide hierarchical representation? Now, when you look at the expression recognition problem, there are major expressions, right? Like sadness, anger, disgust, happiness, and so forth. Now, each of these major expressions can be explained in terms of action units, subtle muscle motions. So you can, decompose an expression that happens around here in terms of what action units over here and so on. So basically, when you learn a dictionary now, you can also provide some structure. For example, happy emotion. There are 43 such action units. See, eyes closed, lips stuck, mouth. These are all local. 25, with lips parting, raised cheeks, and lower lip depressor, and so on. So happy emotion comes when you have a union of cheek raising, lip corner puller, plus 25, which is lip spot. That means you're kind of smiling. Okay? So there is a structure for each of these major expressions in terms of action units. So I want to now learn a dictionary not only for expression recognition, but also for action units. So here you have a hierarchical structure, action units, and they kind of combine locally, a few of them, and they give you the expression. So the dictionaries can be learned simultaneously like that. And so you separate dictionaries for each action unit, and then is then formed using all the individual AU dictionaries and so forth. So when you do this, you will be able to recognize expressions as well as action units, and the performance on two data sets. CK plus is Cohen another data set, and this is the Boston data set, and so on. So if we want, dictionaries can also be used in a hierarchical way. Again, look at this. Combined features, SVM 91.5, nearest neighbor Gaussian mixture model 71. Again, SVM brought it up to 84, 88, had a boost, and our approach was 88.52. This is actually a full transaction paper. So the reviewer said, that's fine. You can probably add more layers and you can beat the existing method. So that's what I'm saying. Don't focus too much on the percentage. Make sure you have a novel way of doing the problem. The reviewers are now warming up to that idea. And so you can, given a particular expression, you can also decompose it and synthesize new expressions to model the former Vice President Dick Cheney's smile. We couldn't. It's a very difficult one, So okay. Now, oftentimes when you have annotations, this is a supervised method. I need to know whose space it is, right, to build the dictionaries and so forth. What if I make a mistake? These days, how do we annotate? We put it on the Amazon chart. We have to train people to do it. And then they do, what if they make mistakes? Even my own students, when we hear them, they just, after a while they get bored. They just kind of, do something, right? They make mistakes. That means if the annotations come with a probability that I think the space, 0.8 Chellappa, maybe 0.1 somebody else, 0.1 somebody else. If you have that kind of ambiguously labeled annotation, can you learn dictionaries? There is a paper that will be published in the special issue, I think it's information forensics and the transactions on information forensics. So we basically showed that we can simultaneously learn the confidence that we can assign to each person the label, and as well as learn the dictionaries using an expectation maximization approach. So I will, and then we tested it on a couple of data sets, last and pi and so forth. So again, this is something you can use for the deep learning thing. So far, what I have shown is how to learn the dictionary for a still image, how to learn it for videos, and how to do across post. Well, I didn't explain this, but there is a paper in ICCV 2013, and then we have the ECCV 2012 paper, and this is the PAMI paper. I think this is now under review for ISBA. That's the mistake. So, you can do a lot of things with dictionaries. In fact, many of the things that people talk about using deep learning, you can do using dictionaries much simpler, lower demands on the training data set, but the performance is not there. So that's the problem. So we have to fix that. Okay. All right. The next topic I'd like to talk about is, I think I'm going to probably finish at 3:30 today. I'm ready to sleep. Yes, so I'll discuss this idea of domain adaptation, and then where is Ajay? Maybe we should get the permission of the boss. All right. This is a problem. This was a data set collected by Berkeley folks in 2010, ECCV 2010. Same objects, right? Cups here, but different posts, different elimination conditions, shoes and so forth. So this is known as the source domain. This is known as the target domain. The idea is, if I build something using source domain, how do I make sure it works in the target domain? There are two things. Domain adaptation is what we call where the X, okay, the labels, the marginals of the labels are not same, but the conditional distributions are same. In machine learning literature, people talk about transfer learning, where this distribution is same, whereas the conditionals are not. So we looked into this problem. We had a paper at ICCV 2011. There was a paper in ECCV 2010 from Senko, Trevor Durrell, etc. at Berkeley. So these are some of the related works. This is a fundamental problem, how to scale your classifier to work on a data with different distribution. Okay? So we want to do an unsupervised version. What does it mean? It means that I know the labels for the source data. I don't know any labels on the target data. So I build something using the source. I should be able to make it work for the target data. Well, as I said at the beginning of the tutorial, if I don't have ID, then the best thing I can do for generalization is a principal component. Yeah, go ahead.
Is that kind of beta class ID? That's why it is kind of problem.
No, it's more like I train my classifier using my test training data set. But then, for example, let's say I used all the frontal cases. But then the data I'm going to work on is all off frontal. So how do I arrange my classifier to work reasonably well on the data set? Or I train using well-illuminated cases, but it is going to be tested on poorly illuminated cases. Or I train my iris classifier using an iris sensor of type 1. Suddenly a new sensor has come. Okay? Even if it is a better sensor, there is no guarantee that you will produce better numbers. That's the thing with all these methods. They are so tuned to the data. Okay, so you have to do a sensor adaptation. If you have some samples from the new sensor, then you can learn how the features go between the two sensors, and you can do a metric MK kind of a thing and do your sensor adaptation. We have a banking paper on that last year. Okay, so people should know that when you use data, if the sensor changes, the data changes. In fact, these images that I showed before were taken from 3 cameras: Amazon camera, DSLR, and a webcam. If you design your classifier using one and then you test it on the other, the numbers go down. How often can you expect your customer to have the same camera? Because you have to ship your camera to him, right? Otherwise, if they change the data, the distribution is different, the performance goes down. So domain adaptation needs to handle that. Okay? So anyway, we want to do unsupervised. Unsupervised means you don't have labels in the target data set, but you have labels in the source. Okay? If I don't have the labels, the best thing I can do is PCA. So you build subspaces for both source, target, put them on a Grassmannian manifold. If you know 2 points on the Grassmannian, you can connect them. It's a standard differential geometry equation. And then you can subsample, you can sample along the geodesics and project, propagate the subspace matrix from source to target. Project both of these samples onto those, construct a long feature vector, and then you can reduce the dimensionality and then do classification. This was our ICCB 2011 paper. It showed up in PAMI last year. Now, okay, so Amazon, you can see how the performance goes down, right? So, we thought we would also try it using dictionaries, okay? Now, how do you do using dictionaries is simple. So this is the using the Grassmannian and so on. That is a paper and it's in PAMI. Basically, for dictionaries, you have to assume there are k intermediate domains, which smooth the transition between source and target. And then you learn the corresponding intermediate dictionaries. You project the source and the data target faces onto these dictionaries, and then you get those sparse coefficients, build a vector, and use it for classification. Now, suppose, how do I explain this? In fact, what is the simplest dictionary method that you can think of? Suppose I didn't tell you anything. I just said, can you tell me a dictionary method that you're all familiar with? PCA? That's a dictionary. Right? I can write any face as a linear combination of pictures, except it's not sparse. Okay? So, if this is all frontal face, this is off frontal, let's assume corresponding to a certain number of intermediate positions, I'm given a lot of samples. Suppose I'm given. Then I can do a PCA. Right? Actually, it goes back to what Pentland and Turek did in the early 90s. Remember eigen poses corresponding to different views, eigenviews and so forth. Just like eigen parts, people also did eigenviews. So if I had a PCA for this, eigen images for this, eigen faces for this, eigen faces, then you give me any 2 faces. I will project onto this, have coefficients. I concatenate all of them. I can compare. And the nearest to pose, the corresponding coefficients will become dominant and will give me the correct ID, hopefully, right? So that instead of doing that, in the case of manifolds, you can actually do it using analytical expressions. Now here, I don't have the intermediate data, so I am actually writing it as an incremental dictionary learning procedure here. This is the initial dictionary, it's a source dictionary, and then I try to build intermediate dictionaries dk so that the corresponding sparse matrix, which will approximate the target data as well as you can, subject to the sparsity constraint, then you can basically construct D0, D1, D2, etc. to dk. Once you have all these dictionaries, 2 faces come, you project onto them, get the sparse coefficients, and you can compare. Okay? How does it work? Well, works on well on high data set across post variation, various performance, and you can add blur, and you can do the adaptation according to that. In fact, even for high, when you add various blur and so on, numbers can go down. As you can see, 25 with KSVD, whereas 70% with this. Now, the other method we also tried, given two data matrix y1 and y2 from source and target, can I learn something that is common? Because so far what I was doing was I was trying to transfer what I learned from source to the target. Now I want to find something that is common. Okay? So here I like to project y1 by using this matrix, dictionary D, corresponding sparse coefficient, projection matrix P2, dictionary D, y2, and then we also add some orthogonality constraints so that we don't get a trivial condition, and you can optimize this. I was kind of smiling when Professor Wang said, a typical computer vision paper, you have to have a methodology, you have to have an optimization criterion and results. So I guess this is a typical computer vision paper then. And you can also add a discriminative term and do this, and we tried it on the Amazon data sets. Look, this is reality. When you train on C and you have to test on A, B, C, get a C. C, there are three cameras, okay, A, C, and D. Look, the numbers, right? This is a serious problem. So when we look at the LFW and we look at the deep learning, everything gets all buried into it because of the large amount of data. But if you really don't have that data available to you to learn, and if you have a small data to go from, the problem is not solved. That's the point I'm trying to get across. It doesn't matter what method you use. It's nothing to do with the dictionary. We have tried a lot of methods. When you change cameras, things can go very badly. Okay, so all right. So anyway, this is Amazon data set, and we have done a lot of other work. We did the result for IRIS in FAMI 2011, and we also KSVD is a dictionary method I talked to you about, but information theoretic learning based method. It appeared in FAMI in 2014, and we have a survey paper on dictionaries for image and video based recognition. And we have an uninvited paper, and this is another concept that we are trying to promote, which is an extension of the tensor phases that some of you may be familiar with. And you can also use dictionary methods for multimodal biometrics. West Virginia has this data set of fingerprints, iris, and things like that. So how do you build dictionaries for the various modalities and combine them and so on? So closing remarks. I think we're going to finish at 3:30. I don't think I can stay around for another half an hour. I'm really sleepy. But we can ask, let's do a Q&A, and then we'll close it. Okay. Data-driven methods are here. They're not new. Right? They've been around for a long time. In between, we went to models. Why did we go to models? When data is small, you can build models and then you can analyze. Okay, so this idea of building models is when there is not enough data. If you have a lot of data, it's not clear to me whether the models are going to play a role as much as it did before. Having said that, data also does not generalize unless you have a model. So we have to start thinking when we use data and when we bring in the model. The fact is, computer vision has models, geometry, 3D things, illumination. Everything has well-defined models. So if we forget all of that, we forget physics, forget geometry, we say, give me 10 million images, I'm going to learn something, it's all going to be fine. I think that is fine too. We should kind of let it go for a while and see what happens. But some of the claims that are made are a little bit difficult to justify, in the sense that once I learn for this data set, I can use it for any other problem. I'm not sure about that. Of course, you can try. You can always use it as initial condition, and then you can bootstrap it, right? Okay, so there are many things that are still loose with these data-driven methods. Now, the dictionary methods seem to have some mathematics that comes from optimization, from signal processing, and so forth. I think when you are working for your PhD thesis, if you decide to go with LFW, no, that's not a good idea, it's done. If you want to do deep learning, you got to start thinking about how to incorporate geometry, how to incorporate illumination variations, how to reduce dependence on the number of training samples, how to figure out what are the optimal number of levels you want to have for a problem, or how do you adapt your network for a different problem. Those are the basic problems you can work on. Then you will be all right. Okay, but remember though, if you look at the Deep Phase 2014 paper at CVPR, when there were alignment errors, numbers went down. How many of you remember that? Okay, so it's still an issue, right? Or if you have fewer training samples for your problem. It's true, somebody did LFW, but you know what? They also gave you the annotations for it. So somebody has to do that. Because the KSVD has to annotate the pictures. Okay, and then we can build that, and so you have 100% performance, then the next problem comes, and if you say I need a lot of data and then somebody has to annotate, then you're starting all over again. So that is somewhat unsatisfactory. Okay, but that's where we are now. We are in a very interesting state in computer vision. If you use this method of features, backprop, etc., you are guaranteed to get some performance. But people are going to question novelty, as Professor Wang said. So, and within a year, there are 4 or 5 groups coming very close to you, so you have to work on it. So, I think it's an interesting time, how to put models into it, and also how to make it foundationally strong. How do you answer the question, hey, you have 60 million parameters, and do you think you have enough data to say something about the parameters? There's no answer, right? So we need to start thinking about those problems. I think they all will make great papers in NIPS and other journals, so I encourage you to work on that. Or if you want to work on dictionaries, please do, but put more layers. Because we decided to stop at 2 and the performance would not be good. You got to add at least 8 layers of dictionaries. Okay? Alright, so I'm going to stop here and take questions. And then we'll have a nice cup of coffee and break.
So the major thing is, how do you design a benchmark that Google and Yahoo can't win at?
Well, the problem is, Brian, they have data and we don't. I'm involved with Google on a project. They have 80 million samples annotated. Okay? So we are pretty sure deep learning is the way to go.
Yes, but if you...
that is basically 24/7 users working with smartphones. What do you do when you get a smartphone? Do this, right? Swipe. There's enough information to tell you who you are based on that. We have a couple of papers in Face and Gestures, 2015. Highly selected tips, 3 sessions. Even there, domain adaptation becomes important. If you swipe in a well-lit room, if you swipe in a poorly lit room, you do it differently. You just try it. Because you're paying a little more attention, the amount of pressure you apply is different. So you have to adapt the sensor. Now, they have collected so much data, 1,000 users, 24/7 a month. They supply CNN. So unless you have, so very interestingly now the leadership has changed. In the sense that not all universities can collect so much data because there's all these privacy issues. That's true with Google too, they can release the data. But actually they can try it out. And if it works, they can put it in their gadgets. We can only collect for 50 users, 100 users. And that's not enough to do a deep learning thing. LFW is a unique case. They produced all of the annotation, so you're able to do that. But you have to think whether you're going to have data, annotated data, for you to do deep learning. Actually, if you look, very few groups are doing this. Hong Kong, Chinese University is a good example of university. Professor Wang is going head-to-head with Google and Facebook. But I think he has a lot of students helping him to create the annotations and all of that, right? The rumor is when Hinton, a PhD student, he spent his 4 years just tuning the parameters of the network. That's why you can't record these things. But that's what we heard. That one PhD student was there spending 4 years just tuning the parameters, which Google bought. Google basically bought the parameters of the network. Over a million, 120 million or something like that, right? So I think what's happening with deep learning network is very interesting because it's questioning some of our beliefs in terms of what a model should be. We all said model should be parsimonious, right? As few parameters as possible. In fact, we have been told the fewer the number of parameters, the better the generalization is. Now, the claim is that we are not overfitting because we have a lot of data, but boy, the number of parameters are large too. So we have to. But I do like them because we have now developed a method for face detection, which I think is the best now in terms of our evaluations, and we are going to publish it a few months from now. And it is kind of like a deep learning. That's the problem. It produces results. So what do you do? Think about it. Yeah, I think I kind of rushed it, but yeah. Go ahead.
Yeah, question about the Authentication. So you mentioned that there are two assumptions for Authentication. So in practice, how do we know that our data satisfies just two assumptions on the prior probability and conditional probability?
Pardon me?
So about the domain application,
Yeah.
so there are two assumptions on the probability and conditional probability.
Yeah. Right.
So in practice, for example, if I want to use the domain shift
Yeah.
on a certain application,
Yeah.
so how should we know that?
I think, see, that's the thing. We are still not satisfied because when I motivate the problem, we say go to PDF, but we never keep track of it. Dictionaries are given, the heuristics given. So we are now looking at how to carry the PDF along with heuristics. Or given samples from both source and target, maybe use a GMM kind of a thing, and then have an idea of whether the marginals or the labels. So we have to bring in probabilistic inference. We have not done that yet. So that.
The third question, you mentioned transfer learning and domain application.
Right.
So basically, we are plotting the two probabilities.
Yes.
So in that case, in your application, why don't you use transfer learning?
We find for the data set we have, the Amazon data set, the other assumption was fine. The PF, I forget which one was that, but the domain adaptation assumption was the right one for the office data set. Yeah. Because of the way that the data was